So let us now consider a set of instructions here, shown here, add, mul, add, etc. And there is a loop here, so it's going to execute multiple times. We have an instruction queue which is going to hold 5 instructions. Then we have the floating point registers as shown in the previous slide in the Tomasulo structure. We have the floating point registers here. Then we have these reservation stations, 3 for the add, 2 for the multiply. We are assuming 1 add unit and 1 multiply functional unit. We also have 2 reservation stations for the integer unit. So this is the example that we are going to consider. So now cycle 1, what is going to happen is the instruction which was at the head of the instruction queue. So if I just go back to the previous slide, the add was at the head of the instruction queue. So basically it is this sequence of instructions, add, mul, the add, sub, etc. So this is the head of the instruction queue. So the first one which is at the head of the instruction queue will get to the reservation station first. It will get dispatched to the reservation station first. So we have the add instruction into its corresponding reservation station. So now what is the content of the reservation station? You have the instruction, the 2 source operands. Now what are the 2 source operands for this add instruction? We have F2 and F0. So we are not showing the rename table here. I'll explain why. F2 and F0. So we are going to look for its sources in the register file. So we have F2 here, which is whose value is 2, and F0 whose value is 0. So we're going to write both of those here in the reservation station. Then we are going to write the destination, which is going to be renamed. Now the destination here is F4, and we are going to rename it to the name of the reorder buffer entry. So what this means is every instruction that is going to get into the reservation station is also going to get an entry in the reorder buffer. So reorder buffer is going to have an entry for each and every instruction that gets into the reservation station. So basically you can think of the reorder buffer as an instruction queue itself, which is going to keep track of which of these is instruction 1, which of these is instruction 2, 3, and so on. So it is going to maintain an order of these instructions. So the first instruction that gets issued or dispatched into the reservation station will also get an entry in the reorder buffer. So what do we put in the reorder buffer? This is the reorder buffer entry, which is 0. That's the first entry. We put in the instruction name, which is add, and we also put in the destination here. The destination is F4. So in a way, we are actually maintaining a sequence of instructions, and we are also using this as a rename table because we are renaming the destination F4 to the name of the ROB entry. So the ROB entry is ROB0. So we have renamed the destination F4 to the ROB entry ROB0. Okay, so these are the sequence of events that have happened in cycle 1. And we make another change here. F4 in the register file is also going to have a rename entry here, which is ROB0. So we are maintaining this register and the register which has been renamed. So this link we are maintaining in multiple places. 1, we are maintaining it in the reservation station. 2, we are kind of maintaining it in the ROB itself. 3, we are maintaining it in the register file. So these are the 3 places where we have maintained this connection between the register or the destination register and the ROB entry. So now this is the head of the ROB. This is a head pointer, and there's also going to be a tail pointer, which is, in this case, it is going to just point to the next instruction or the next entry. So now let us see what happens in cycle 2. Cycle 2, we start with the instruction queue again. The next instruction to be issued is the multiply instruction. So that gets issued into the reservation station. I should probably use the name dispatch because that is the right technical term. So we dispatch the instruction from the instruction queue to the reservation station. So we have the multiply reservation station here and we dispatch it there. So now we do the same steps. We maintain the sources. First source one is F4. So when we look for F4, we look for F4 in the register file and we know that it has been renamed to rob0. So we write rob0 here. And then the second source is F2. We look for F2 and we find the value there, that is 2.0. We put it there. Then we do the same thing again. We make an entry for multiply in the rob. So basically we uh, go to the second entry, which is rob1. We write the instruction, we write the destination, and we rename the destination to rob1. We also rename F8 in the register file to rob1. So now, after all of these steps, we are now ready to go to the next one. At this point, we should also note that we are not keeping track of the latencies of the instructions and how much delay is present for executing the ad and so on. But because our current focus is on how the rob works, so we can assume that parallelly what is happening is the reservation station has found that the sources are already available, so it is issued the add instruction to the functional unit and the add operation is going on. So we can assume that in the background. So in the meantime, when we move to cycle 3, we perform the same steps. We dispatch the third instruction add to the reservation station. We accordingly find the sources F8 and F6. We find that they are rob1 and 6.0. Then we make an entry in the rob, which is corresponding to rob2. We rename F6 to rob2. And now we do the same renaming in the register file. In the meantime, the add is executing. We assume that in the background. Cycle 4, I'm not going to repeat. We take sub and we put it in the reservation station. We also make an entry in the rob. We rename the destination. Now it is important to note here that F8 has already been renamed once. F8 was previously renamed, we see here, to rob1 entry. And now what is going to happen is F8 has been again renamed to rob3 because it already has, it has been now assigned rob3. So now, rob1 has been eliminated from the register file, but we still maintain this F8 in the rob1. So basically, although you've disconnected F8 and rob1 from the register file here, we somehow still maintain that connection here in the reorder buffer, and we also maintain that connection here. So we'll see in future, in the next few cycles, we'll see why this is important. So now in the meantime, we assume that the ad is still going on. And let us assume at cycle 5 that the ad has completed and it has issued, it has released the result 2.0. And it is also released the tag along with it, which is rob0. So rob0 equals 2 gets broadcasted on the common data bus or the CDB. Now this CDB is connected to the reservation station and therefore we also get the value here. So if I just go back to the previous slide, so we have rob0 here. So wherever you find rob0, it is going to get replaced with 2.0. So you see here rob0 getting replaced with 2.0. At this point, we can free up this reservation station entry. We are not going to rename this because it is a destination. We are only going to change the, we are only going to capture 2.0 wherever you have the sources in the reservation station. So in the meantime, we should also note that this multiply cannot get issued till this point, in fact, till the next cycle, because it was waiting on Rob 0. So now, parallelly, what is also happening is the common data bus is going to transmit this 2.0 here. So this 2.0 is going to come and sit here at the head of the Rob, because this was the Rob 0 entry. So 2.0 is captured here. And we also note that there is no connection between the CDB and the register file, so I cannot go and write 2.0 here. So to summarize this cycle, we have broadcasted 2.0 rob 0 equals 2.0 on the common data bus because add has finished. And wherever you had the sources as rob 0, you're going to replace that with this 2.0. So in the next cycle, this multiply can issue to the functional unit and can start executing. We are also capturing the rob 0 value in the rob itself, and we are not directly writing the rob value to the register file. So now let us see what happens in this cycle 6, which is the next cycle. This is interesting because we have now released the reservation station entry because we have completed writing the value of rob 0 to the rob. So now as a last step, we are going to release this entry in the rob as well. And before we release the rob entry, we are going to write to the register file. So where are we going to write it to? So if I just go to the previous slide once, rob 0 is F4, and that is what you have here. Rob 0 equals F4. So we are going to now write the value from this rob to this register file. So basically we're going to match wherever rob 0 is. So the rob 0 is present here. We're going to replace that with 2.0. So basically 2.0 is the value. And we eliminate this entry rob 0 because we are no longer using that entry. We have already computed the value. So we write the value here and we clear this entry here. This was the rename entry. We clear it. We also clear the rob because we are done executing it. At this point, we move the head pointer to the next instruction. So this is important because this is a circular queue. So, and this is a buffer which has limited number of entries. Like here, it has 7 entries. So once you are done with 6, you are going to go back to 0. So that is why it is called a circular queue. So now to summarize this cycle, we release the reservation station first. We write the value of rob 0 to the place in the register file which was renamed to rob 0. And we clear the entry rob 0 in the register file. We clear the entry here in the rob and update the head pointer to move to the next instruction. So in the meanwhile, what is also happening is the next instruction sub and branch have got dispatched to their respective reservation stations. So now let us see what is happening in cycle 7. Okay, let us once go back to the previous cycle. We should just note that the multiply has probably been issued to the functional unit and it is executing. It has probably been released in cycle 6. And now let us assume, for example, in cycle 7, the multiply finishes and it is going to write this value rob1 equals 4.0 onto the CDB. We now repeat the same steps. We broadcast this value to all those reservation stations which are waiting on rob1. So basically it is going to come and get captured here because this add has been waiting on rob1. You can also see it here. The add has been waiting on f8. So that is rob1. So that is going to capture that value and start using it in the next cycle. Then it is going to come and get captured in the rob itself, and its value is 4.0, and that is at the head of the rob. So this is happening in this particular cycle. And then, of course, the branch has probably finished, and then the next instruction add is going to get issued or dispatched to the uh, reservation station. So while all of this is happening, what is interesting to note is now when you want to write the value of rob1 equals 4.0 to the register file, so where are we going to write it? So that is an important point. So now here we can realize the importance of the reorder buffer. So the reorder buffer is having the connection between rob1 equals f8 equals 4.0. So now if it tries to match for rob1, it cannot find rob1 in the register file because it has already been again renamed to rob3. So what it should do ideally is it should try to match the destination f8. It finds f8 and it's going to write the value 4.0, but it's also going to try and see if its rename value is rob1. So if its rename value is not rob1 and something else, what this means is that this destination has been renamed again by some other instruction, and therefore it is not going to clear this rob3. So if we look back to the previous uh, instruction here, the add instruction, we cleared the rob0 rename entry here. We updated f4 to 2.0 and we cleared this rename value. We had rob0 here, we cleared it. That was because rob0 was equal to f4 at this point in time. But if you note here in this particular cycle, rob1 is not f8 in this register file. In the register file, what we have is rob3 equals f8. So what this means is that some future instruction, such as this, which was a rob3 entry, has renamed this f8 again. That means it was rob1 and it has been renamed to rob3. And therefore, we are not going to clear this entry here. So we are going to update the value of f8, that's fine. And we are going to leave this rob3 as it is. So these are the important steps here. So that's what I've written here. We write back f8 to the register file. We are also going to clear this head entry in the rob. What is happening in the register is we're going to check if f8 is waiting on any new value. Yes, it is waiting on a new value, which is rob3. And therefore, we're going to retain that new name, which indicates that f8 was renamed again. But you should also note that this f8 equals 4.0 is not going to be used by any instruction. So f8 equals 4.0 from the register file is not going to be used by any instruction because that f8, if at all it is needed, will be directly taken from the CDB to the reservation station. But this is only to manage and handle exceptions that we write back the correct value of the architectural register to the register file. So this is how the ROB works. So how this is going to continue, I've not shown it here. You can go ahead and complete this if you need. So what is going to happen next is the add instruction is going to complete, and F6 is going to get written to the architectural register file, and then sub is going to get written.